So far we've dealt with constant forces, but now let's think about what happens when the force varies. So if the force varies, you have to use an integral, is basically the short answer. So the work is the integral from some initial position to some final position. There's your displacement, initial to final, of the force dotted with some differential change, some differential displacement. Okay? This is not a new formula for the work. This is just a more general formula for the work. The one we had before, F dot delta R displacement, was when the force is constant. If the force varies, you got to do a bunch of little delta R's and add them up. That's what an integral is, right? So the best introductory way to show this is the mass on the spring. So let's imagine we have a spring here, and it's coiled up and compressed and pushing on a block, and everything is frictionless. So the block is going to feel a spring force like that, pushing it this way because the spring's natural length is there. When this position is here, the spring is natural length, no forces. We've pulled back. We know F equals minus kx, so it's going to push that way. So as the spring pushes the block from one position to another, let's calculate the work it does on the block. All right, so to do that, we need the force of the spring. Let's do full units here. Let's do full coordinate system, y, z, x, y, z as usual. In the x direction, what is the force? According to Hooke's law for forces, it's minus k times the x position. It's really x minus, or it's the displacement from the natural length, but I put the natural length at the origin. So we just call it minus k times x. Plus 0, j hat plus 0 k hat. We don't really need those. This is obviously one-dimensional, but we'll be complete. So we have F, we need dr. So dr, you can really just think of as the differentials in each dimension. Right? It might move a little dx I hat. It might move a little bit of motion in the j hat dy plus dz k hat. So we brought in those other differentials, but when we take the dot product, they're going to go away. All right, so because we care about f dot dr. Right? So f dot dr, gone. You know, these are 0, 0. It's really just minus kx dx. Don't need the unit vectors anymore because we took a dot product. There you go. So now we just do our integral. The work equals the integral, and we need limits. So let's see, we're going to talk about the work as the spring pushes it to here, because then that's all it's going to push it. Then it'll fly away. The spring will do whatever it wants to do. If it has no mass, it'll stop or keep going. We want to think about the work from here to here. So let's say it starts out at the position minus d. All right, we're going to push it through a distance d. So it starts at minus d and pushes to 0. So initial to final, it started at minus d and pushed to 0 of minus kx dx. All we got to do. Then you have to know how to integrate. So vector-based or physics-based calculus, hopefully you know how to integrate that. It is equal to minus 1/2 kx squared evaluated from minus d to 0, which we plug in 0, we get 0, minus, we plug in minus d squared is d squared, so minus of minus 1/2 kd squared. And of course that becomes positive to 1/2 kd squared. The work that the spring did on the object. Right? So notice, it's not just the force kx times the displacement d. Right? That would be kdd or something, kd squared. Right? The half shows up because it's an integral, because the force was big, but then as you add it up, the force is less and less. The work it's doing is less and less. So the half shows up. In general, if you wanted to write this and really not do a specific case of a limit, you could also write it this way. You could say the work of a spring on a mass, you could say it's just 1/2 k x final squared minus 1/2 k x initial squared, if you define those positions with respect to the rest length of the spring where the forces are 0. Then you could always find one that way. Now we're going to cover the work kinetic energy theorem. Now let me get some off my chest. I don't like theorems. They often make things more complicated than they need to be. And really here we're just talking about conservation of energy. I also don't like coming in this early, only with kinetic energy. We should just go straight to the full conservation of energy. But what I do, I think it is a good idea to go ahead and start slow. Start with work kinetic energy, because it'll help us think about all these weird terms that show up about the system and external, internal, blah, 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 blah. So let's go ahead and do, with that inspiring caveat, let's do the work kinetic energy theorem. Okay, here we go. So external work. So we'll have to talk about what external work means. Work on a system, we're going to talk about what system means. External work on a system equals the change in kinetic energy. And now here come the little assumptions. This is just the very early thing where we're considering very few things about energy. If it only speeds up. More will happen later, but right now we're just talking about something speeding up in 1D. More will happen later, and we will drop the kinetic part. Okay, so what this really is saying is this very simple idea where if I push on this cart, it's going to speed up. I'm going to push, I'm going to do work, F dot displacement, and the kinetic energy is going to increase, right? Just like we saw before. There it goes. All right, yeah, okay. So let's look at that. Oh, there we go. Let's look at that. Here's the ground. Here is the cart. And here is my finger pushing the cart. So I applied FP, and the cart moved displacement delta R. So as we saw before, of course, I did the work F dot delta R. But now, let's look at these other words, right? External and system. So in this case, the system, the way we're going to analyze it, the system is the cart. The cart is the system. Just that object. This little dashed line that defines the system moves with the cart. Okay? And in this case, my hand applies external work. We have a system, I applied work to it. Let's see then, what is a mathematical expression then of the work kinetic energy theorem? It is that the work external that I applied with my hand equals delta K of the system. That's really all it is. If you have a system, something comes in and does work, of course, as you would expect, the kinetic energy is going to increase. You could also say it's like this, the work external, if you want to get into the details, K final minus K initial of the system. Final kinetic energy is greater than the initial kinetic energy. So this isn't so bad, but this gets confusing. We talk about work and system, internal, external, and signs. It gets confusing later. So that's why I wanted to start us out with this very simple case. So now let's check our signs. Let's see, the external work. Was it positive, negative? It was positive. In addition to the external work being positive, we can now look over here and say delta K of the cart should be positive. So K should have increased. And sure enough, if we think about the demonstration, yes, the kinetic energy increased. It was at rest, and it picked up speed. So again, there's a very simple system to start us thinking about external work, internal work, what's in the system, what's out of the system, who all's in the system, etc. As I said, one hard part of keeping up with these energy work theorems is the negative signs. So let's ask the question, can you have negative work? Yes, you can, because delta K, the change in kinetic energy, can be negative. just not k. Right? The kinetic energy is always positive or zero, but of course you can have a change in kinetic energy. So to help us think about this one, let's say a mass at V collides with a spring. And let's think about what happens. What is the deflection? The maximum deflection. Okay, so we can draw that real quick. Let's see. So we're going to think about it this way. We'll have an x-axis like that. Here's a wall that the spring is attached to. And here is its natural resting position at 0 of the x-axis. The mass is going to come flying in like this at velocity v. So you can imagine what's going to happen is the spring will push and it'll bring the mass to a stop. And that's the question, is how far does it go in to bring the mass to a stop? If you have a head for conservation of energy and you've done these before, you know that you just set 1/2 mv equals, set 1/2 mv squared equals to 1/2 k deflection squared, and you're done. But let's think about it carefully in terms of systems and external and internal and positive and negative, and see if we can do it in careful detail. To do it in careful detail, we have to define the system. In this case, the system will just be the mass. All right, so the system is the mass. Therefore, the force of the spring is external. So if we set it up that way, let's see if everything makes sense according to the work kinetic energy theorem. So external work equals delta K, the change in kinetic energy. So what would be the external work in this case? Well, it is going to be the integral of F dot dr, or the force dotted with the displacement. So as this thing pushes into the spring, the force is negative x, right? So the force is minus kx, and that is times the displacement is in the positive x direction, right, dx, for the integral. Okay. I didn't do the full vector part, right? But if we thought of the force as a vector this way and the displacement as a vector that way, they're opposite directions. That's why it comes out with a negative sign. So minus kx dx is that integral, and we're going to integrate from 0 to, let's just call it big D, the displacement. 0 to d. That's how far it gets. Okay. So that's one side. The other side is delta K. That must be the kinetic energy minus the kinetic energy initial, final minus initial of the system. Right, the system being just the mass. The mass is kinetic energy. All right, well, let's do our integral. This is minus 1/2 kx squared, evaluated from 0 to big D. And this is, let's think about it. It started out, the final kinetic energy is 0. We're figuring out how far it deflects before it stops. So that's 0. And then minus the initial kinetic energy is what it had when it first hit the spring, and that's just 1/2 mv squared. All right, so when we evaluate our limits here, this is minus 1/2 k d squared. Minus 1/2 k d squared equals minus 1/2 mv squared. Oops. And you can see the minuses become pluses. And you can see it is just that simple idea. Oh, just take the kinetic energy and equate it to the energy that gets dumped into the spring. But here we've done it, I'd say, a little more carefully, right? And we've thought carefully about our system. Everything makes sense. But notice the work was negative, right? You do negative work when you push on something, but it moves against the push. Right? Before I did positive work when I pushed the mass, because I pushed along the direction that it moved. Here the spring is catching, right? And the spring is doing negative work. And you do negative work because you have a lowering, a negative, in your change in kinetic energy. The thing lost kinetic energy. So the energy, or the work kinetic energy theorem part makes sense. I guess we should finish this. The 1/2 go away, and this comes over here, and V becomes, oh no, I'm sorry, xd is what we're solving for. The d, the displacement, becomes the square root of m over k times v to finish it. So there's the answer. I can also show you negative work by pushing the cart. So you won't believe how good I am at this. So I'm going to have the cart come, and it's going to come, and I'm going to use my finger to apply negative work. I'm going to push on it. I'm going to push this way. The cart is going to displace this way. I'm going to bring it exactly to 0. Practical effects.